I have this old postal scale, which measures weights in pounds. And one day a few years ago, I took it on a trip on an elevator, loaded up full of textbooks. And I think watching the apparent weight of the books as the elevator goes through its trip can tell us a lot about how forces add together and also what scales actually measure. Let's take a look. So let's go through that step by step. So here's the books on the scale right at the beginning before the elevator started moving. And it's registering 14.5 pounds. Given that this is the typical way we use scales, we put them in a room that's not moving and put stuff on them, I'm going to say that the books actually have a weight of 14.5 pounds. So we press the button, and we get some fluctuation. The arrow seems to go back and forth, and that's because the spring is rocking up and down. But 13 pounds seems to be the average as the elevator starts to move downward. So we have to think about why the books appeared to change their weight. But let's let it keep running. After a short time period, it's back to being 14.5 pounds. It stays that way for a while. Then it rocks up at the very end of the motion, and it gets as high as 17 pounds for a little bit. And then, right as we're hearing the elevator beep because it's at the floor, in other words, we've stopped and it's ready for me to get out, it goes back to 14.5 pounds. Okay, so I've gone through and converted those scale readings from the US unit of pounds for force into the SI unit of newtons. So at the beginning, when we were at rest, the scale was reading 64.5 newtons. Then we started to accelerate down, and during that acceleration period, the scale dropped its reading to 57.82 newtons. Then the elevator ran at constant speed for a while, and notably during this period, it was back to 64.5 newtons, just like its usual reading. And then when we stopped, the reading went up, and for a brief period it was at 75.62 newtons. So what's going on? We have to think of the free body diagram for these books as it's running. This is the scale under its usual conditions, and we can see that 14.5 pounds is the weight of those books. But the scale's not measuring the weight. The scale is relying on the fact that under the usual conditions, the normal force of the scale and the weight of the books balance. The scale knows how much it's being compressed. There's a spring inside to tell it that. It knows what the normal force is. So scales only give you an accurate reading for weight if weight is equal to the normal force. What we had going on here was we had the normal force changing as the elevator was accelerating. So what we need to do is we need to try to figure out what that acceleration was doing to the normal force. And we also can use this apparent change in the scale, this change in the normal force. We could figure out the elevator's acceleration from it. We'll start these like we start all force problems with a force picture or free body diagram, and then we'll try to solve for acceleration. At the beginning, we're back where we were before. We had a normal force, and we had the force of gravity. And they're balanced because that elevator was standing still, nothing was going on, and since the books weren't moving, there must have been no unbalanced pull up or down. So we translate that into an equation, something we can solve with, by just writing Newton's second law. We just basically write sigma F is ma. This case, it's actually pretty simple. We got to pick a direction. I typically like to call up positive. We'll call down negative. And that means that we replace sigma F with Fn. Notice it's plus because it's up, minus Fg. And all that equals ma. But what's A? Nothing's accelerating. Nothing has any change in its motion at all. A is 0. So we're left with Fn minus Fg is 0. And not surprisingly, Fn equals Fg. So that's kind of interesting. What we intuitively thought, that the upward and downward poles must be identical, actually ended up being what happened. What about these periods? Well, what was going on there? In those periods, we actually had the elevator accelerate. So let's start with this one. We know the force of gravity has the same size because the books didn't lose any mass. The Earth didn't pull on them less. So what must have dropped? Just that normal force. So this kind of looks like a tug of war that the top force is losing. And it's got to be, because we were not in motion. We were objects at rest. We wanted to stay at rest. And all of a sudden, we accelerated downwards. That means gravity must have won. It's not that gravity got bigger, it's that the normal force got smaller. The whole floor fell out from under us. So we'll have to add in a little downward acceleration. So what's our sum of force equation look like there? Still sigma F equals ma. This part's the same too. It's still an upward normal force minus downward gravity. But now A is not 0. In fact, we expect A to be some sort of negative number since it's pointing down. Let's find out what it is. So the normal force apparently was 57.82 newtons. What was gravity? Well, let's just use what the scale said when the scale was working normally. Minus 64.5 newtons. And all of that equals ma. So 57.82 minus 64.5, that's minus 6.68 newtons. And that equals ma. Since I got the mass as 6.59, that means now I can solve for what the acceleration was. So all we got to do is divide both sides by 6.59. And we end up with minus 1.01 meters per second squared equals acceleration.
I'm going to let you solve the other two on your own, so just pause the video, and when you're finished, you can come back and see the completed ones. Okay, so here's our final answers. And I think this middle one, when we were going at constant speed, I think that's a really nice demonstration of Newton's first law. Objects in motion stay in motion unless acted on by an unbalanced force. We didn't have an unbalanced force here. The normal force that the scale was reading was right back to gravity. And basically in this earlier period, because we accelerated down, now we were an object in motion. So to continue moving down, we didn't need any more acceleration. We didn't need any more unbalanced force. Eventually, though, we were an object in motion and we needed to stop. So we did need an unbalanced upward force in order to stop us.
It looks complicated, but it's a process. Sigma F equals ma becomes your list of forces. And the point of that is that all the forces there together are what cause the acceleration. So this is the way of taking them all into account. Picture sigma F equals ma, list your forces. You'll always have enough equations to solve. And once you've got this written out, as scary as this looks, it goes back to really being an Algebra 1 type problem. We're going to practice this a lot. There'll be a lot of examples for you to do. And if you get comfortable with this, it's really going to have you set up well for problem solving for the whole rest of the year.